Good morning, students. In the last video, we dealt with the packing efficiency in different structures, HCP, CCP structures, BCC structures, and primitive cubic unit cell. In this, and also we dealt with the calculation of unit cell dimension formula, that is density of a unit cell, D equals to Z into M by A cube into NA. Let us see today assignments on the calculation of unit cell dimensions there. So let us start with our first question. Here it is there on my computer screen. The first question I read out. X-ray diffraction studies show that copper crystallizes in a FCC unit cell with an edge length of 3.608 into 10 raised to minus 8 centimeter. In a separate experiment, copper is determined to have a density of 8.92 gram per centimeter cube. Calculate the atomic mass of copper. So here you need to calculate M, capital M, molar mass of copper you need to calculate. We know that in an FCC unit cell, the number of atoms that are present per unit cell, that is the value of Z in FCC is equal to 4, right? We have read this previously and many times I have told you that number of atoms present per unit cell, that is the value of Z in FCC equals to 4. And the calculation of density, that is D, is dealt with in the formula. I dealt with this in the last video. So here we are applying that formula. So D equals to Z into M upon A cube into Na, where Z is the number of atoms that are present per unit cell. Here the value of small z is equal to 4. M is the molar mass of the substance. A is the edge length. A cube being volume. And Na is the Avogadro's number, whose value is 6.022 into 10 raised to 23. So here we need to calculate M. So M will be equal to D into A cube into Na upon Z. So when we substitute the value, density is given here as 8.92 gram per centimeter cube. Avogadro's number, the value is 6.022 into 10 raised to 23 atoms per mole. And the edge length is given here as 3.608 into 10 raised to minus 8 centimeter. We need to take the value A cube. So we'll take 3.608 into 10 raised to minus 8 centimeter whole cube upon 4. The value of Z here is 4. So on substituting these values, we get the answer there as 63.1 gram per mole. So the atomic mass of copper comes out to be 63.1 unit. This is how you will work out this problem. Let us come to the second problem. The second problem is again silver forms CCP lattice, and X-ray studies of its crystals show that the edge length of its unit cell is 408.6 picometer. Calculate the density of silver. Atomic mass is given here as of silver, it is given as 107.9 units. So here I give you a big hint first. That is, you need to convert the unit picometer either to meter or to centimeter. We know that 1 picometer is equal to 10 raised to minus 12 meters. Or it is also equal to 1 picometer is also equal to 10 raised to minus 10 centimeter. So here you see silver crystallizes in CCP lattice. So the value of Z is here equals to 4. Right? Edge length is given here as 408.6 picometer. Convert that to either meter or centimeter. So here, if you're calculating density in gram per centimeter cube, then convert picometer to centimeter by multiplying 408.6 picometer into 10 raised to minus 10, converting it to centimeter there. So we convert picometer to centimeter by multiplying it by 10 raised to minus 10. Molar mass is given here as 107.9 gram per mole. U stands for gram per mole. And then we can put it in the formula of density. D equals to Z into capital M, that is molar mass, upon A cube into Na. Na value is Avogadro's number and its value is taken there as 6.022 into 10 raised to 23. On substituting, I have given you the answer. You should get the answer there as 10.5 gram per centimeter cube. That is the solution how you will be doing. So let us come to the third question. The third question is, an element has a body center cubic structure with a cell edge of 288 picometers. The density of the element is 7.2 gram per centimeter cube. It is given there. How many atoms are present in 208 gram of the element? That is the question that is given. Here you keep it in your mind. Element has a BCC structure. So the number of atoms that are present in BCC structure is equal to 2. So the value of Z there is equal to 2 there. That is the one you need to remember in your mind. Then cell edge is given 288 picometer. You need to multiply 288 into 10 raised to minus 10 by converting picometer to that of centimeter. Density is given here as 7.2 gram per centimeter cube, right? So using the formula of D equals to Z into M upon A cube into Na, first calculate the molar mass of the element by putting in the formula which you can see in by the cursor which I am showing you. M, capital M, is the molar mass, that is equal to density into A cube into Na upon Z. D value is given, A value is given, Na you know it is 6.022 into 10 raised to 23 atoms, and Z value, since it crystallizes in BCC structure there, the value of Z you will take here as 2. Correct? Till here I hope you have followed. Let us, after putting the values, all the values, substituting the values that are given, we get the molar mass to be 51.8 gram per mole. So on putting all the values D, A cube, Na divided by Z, you get the molar mass of the solid substance to be 51.8 gram per mole. Then you see how to substitute. This is the second step which you are doing. 51.8 gram of the element contains 51.8 gram of the element contains how many atoms? 6.022 into 10 raised to 23 atoms. Therefore, 208 gram of the element will contain, this is the unitary method by which you will be solving, 6.022 into 10 raised to 23 divided by 51.8 into 208 there, and you get gram gets cancelled and you get the value here as 24.16 into 10 raised to 23 atoms there. So 208 gram of the element contains 24.16 into 10 raised to 23 atoms there. You will practice this in your assignment copy. Let me come to the fourth numerical problem. The question is, an element with molar mass 2.7 into 10 raised to minus 2 kg per mole forms a cubic unit cell with edge length of 405 picometer. If the density is 2.7 into 10 raised to 3 kg per meter cube, what is the nature of the cubic unit cell? Now firstly you see what are the given things, values that are given here. So the first given value is molar mass, M, capital M. It is equal to 2.7 into 10 raised to minus 2 kg per mole. With cell edge length is given there as 405 picometer. So you need to convert this to meter there, multiplied by 10 raised to minus 12 meters. So edge length here will be equal to 405 into 10 raised to minus 12 meter. Density is given here as 2.7 into 10 raised to 3 kg per meter cube. you need to calculate the value of Z there, number of atoms that are present per unit cell. You will put in the formula of density calculation, D equals to Z into M upon A cube into Na, where Na is your Avogadro's number, A is your edge length, A cube being volume. Small z you need to calculate, density is given and molar mass is also given. So the value comes out to be 4. But the question is, you don't need to leave the answer there by writing 4. If you write 4, your marks will be deducted. So there you need to complete the answer. The question here asked is, what is the nature of the cubic unit cell? So you will write the nature of the cubic unit cell, either it is FCC or CCP structure. That you need to write there. You can see my cursor movement there. It is FCC or CCP cubic unit cell it belongs to. Look at my fifth question. Question is, silver crystallizes in FCC lattice if edge length of the unit cell is 4.07 into 10 raised to minus 8 centimeter and density is 10.5 gram per centimeter cube. Calculate the atomic mass of silver. So here it's again very simple. Silver crystallizes in FCC lattice means the value of Z here is equal to 4. Edge length is given 4.07 in 10 raised to minus 8 centimeter. Already it is given in centimeter, so no need to convert. Density is also given 10.5 gram per centimeter cube. You need to calculate the molar mass. So just put it in the formula and calculate D equals to Z into M by A cube into Na. So you calculate the value of capital M. It should come out to 107.09 gram per mole. Let us look at the sixth question there. Question is, copper crystallizes into FCC lattice with edge length 3.61 into 10 raised to minus 8 centimeter. Show that the calculated density is in agreement with the measured value of 8.92 gram per centimeter cube. So you need to calculate the value of density there. D equals to, you need to calculate Z into M upon A cube into Na. So you will see whether the density which you have calculated is in agreement with this measured value of 8.92 gram per centimeter cube or not. FCC value, Z value is there equal to 4. So you will take and accordingly you will just see and whether it is in agreement with the measured value of 8.92 gram per centimeter cube. Look at my next question. Question is, niobium crystallizes in BCC structure. BCC structure, there is the hint that is given, that is the value of Z which you will take there is 2. Density is 8.55 gram per centimeter cube. Calculate atomic radius of niobium using its atomic mass 93 units. The answer there is reflected. It is 143.1 picometer which you should get. Please solve these problems, and if you have any doubt you can consult me. I am there to help you. Now let us come to the next topic, a very important topic of this chapter, that is imperfections in solids. So imperfections in solids are basically the defects which are seen in the solids there. So these defects, actually I have taught you that although crystalline solids have both short range as well as long range order, although they have long range as well as short range order, they are not perfect. I mean to say they are not perfect means they have defects in them. So imperfections are basically defects, and they are irregularities in the arrangement of constituent particles. So imperfections in solids are the defects that are basically irregularities in the arrangement of constituent particles, and defects are of two types. First one is point defect and the second one is line defect there. So we'll be reading in detail about point defects only, but you should know what are point defects and also what are line defects there. So point defects are irregularities or deviations from ideal arrangement around a point or an atom in crystalline substance. Once again, I repeat, point defects are irregularities or deviations from ideal arrangement around a point or an atom in crystalline substance, whereas line defects are the irregularities or deviations from ideal arrangement in entire rows of lattice points. And these irregularities are also called crystal defects. So both these irregularities, that is point defects as well as line defects, are also called crystal defects. But we shall confine our discussion to point defects only. So we'll see the first type of point defect, that is the point defect. They are of three types. They are classified into three types. First is stoichiometric defect, second is impurity defect, and third one is non-stoichiometric defects. So I repeat once again, point defects are classified into three types. First one is stoichiometric defect, second is impurity defects, and third one is non-stoichiometric defects there. I deal with the first type of defect, that is stoichiometric defects there. Stoichiometric defects, basically they do not disturb the stoichiometry of the solid. So that's why they are come under this heading of stoichiometric defects. They do not disturb the stoichiometry of the solid, and so they're also called as intrinsic or thermodynamic defects. Basically they are classified again into four types. A vacancy defect, the first one being, second one is interstitial defect, third one is Frenkels defect, and the last one, the fourth one, is Schottky defect there, or you can say Schottky defect. Schottky or Schottky, both are correct. So basically stoichiometric defects are classified into four types: vacancy defect, interstitial defect, Frenkel defect, and Schottky's defect there. So first we deal with vacancy defect. Before we go for it, you should know the first two defects, that is the vacancy and the interstitial defects, are seen in case of non-ionic solids. So vacancy and interstitial defects are seen in case of non-ionic solids, and the next two, that is Frenkel and Schottky defects, are seen in case of ionic solids. So there are four types of stoichiometric defects that are seen. The first two, vacancy and interstitial defects, are seen in case of non-ionic solids, and the next two, that is Frenkel as well as the Schottky defects, they are seen in case of ionic solids. We'll see one by one all the types of defects. The first I start with is your vacancy defect. So you can see here on the slide, vacancy defect, when some of the lattice sites are vacant. You can see this is a figure that is being shown, figure 1.23, vacancy defect. You can see the yellow ones that are there, the yellow spheres, they are your constituent particles, and when some of the lattice sites, the white one which you can see, they are vacant, the crystal is said to have vacancy defect there. So when some of the lattice points are missing from that of their regular point lattice site, the crystal is said to have the vacancy defect, and this type of vacancy defect decreases the density of the substance. So vacancy defect, remember in your mind that it decreases the density of the substance there. The question comes in the exam there. The question is, what type of defect can arise when a solid is heated? So when a solid is heated, it results in giving you vacancy defect. Next part of the question, you see, which physical property is affected by it and in what way? The physical property that is affected is density, and it decreases the density of the solid as a whole. That is the answer you'll be writing. So vacancy defect is arising when a solid is heated and density gets affected by it, decreases the density of the solid. Let us come to the second type of stoichiometric defect, and the second type is interstitial defect. There, this is seen in non-ionic solid. Once again I say, vacancy defect and interstitial defect are seen only in case of non-ionic solids. So interstitial defects, when constituent particle occupy an interstitial site. So you can see the interstitial site, the constituent particles are occupying the interstitial site. Interstitial sites are empty spaces that are available. So the constituent particle is occupying those sites, interstitial sites there, and the crystal is said to have interstitial defect. So since there are more number of crystals that are present in this interstitial defect, the density of the substance increases there. It increases the density of the substance as a whole. So that is interstitial defect. These two types of defect, that is vacancy defect and the second one interstitial defects, are seen in case of non-ionic solids, and they come under heading stoichiometric defects. The third type of defect which I am going to show you, third type of defect is Frenkels defect there. So in this Frenkels defect, in this type of defect, the smaller ion, that is usually the cation, the smaller ion, usually the cation, +1. Cations are marked with plus and anions are marked with minus. Usually the cation is dislocated from its normal site and it creates a vacancy defect at its original site, and it occupies the interstitial position there, and it occupies the interstitial position. It creates an interstitial defect at its new location. You can see in this diagram here, the cursor movement, you see the plus part is missing from this diagram. Usually the cation is missing, dislocated from its normal site, and it creates a vacancy defect there at its original site and an interstitial defect at its new location. So you see it has occupied this interstitial site and this has created an interstitial defect at its new location there. So this is Frenkels defect. Smaller ion is usually dislocated from its normal site and it creates a vacancy defect at its original site and it occupies a interstitial position there. Then these Frenkel defects are also called as dislocation defect. It does not, the effect of density, it does not change the density of the solid. It does not affect the density of the solid there. Does not change the density of the solid. The next characteristic feature of this defect is Frenkel defect is shown by ionic substance in which there is large difference in the size of the ions. So Frenkel defect is shown by ionic substances in which there is large difference in the size of the ions. Usually the cation is small and the anion is large in nature there. Examples of Frenkel defect you have to remember in your mind. It is zinc sulfide, silver chloride, silver bromide and silver iodide. ZNS, AgCl, AgBr and AgI, due to small size of zinc and silver ions, they show this type of defect, that is Frenkel's defect is seen. Let me come to the fourth type of defect, that is Schottky's defect. Schottky or Schottky's defect. It is also basically a vacancy defect in ionic solids, and in order to maintain the electrical neutrality, the number of missing cations and anions are equal. So equal number of anions and cations are missing from their lattice point. Here you see the plus is missing, here you see the minus is missing there. So here you see minus is missing and here you see plus is missing. Look at my cursor movements. So equal number of anions and cations are missing from their lattice sites to maintain the electrical neutrality of the solid. The effect of density is it decreases the density of the substance. So Schottky's defect, there is decrease in the density of the substance, and this type of defect is shown in ionic substances in which the cation and the anion are almost similar size. They have got almost similar size. The size of the anion and the cation, they are almost similar. Examples are sodium chloride, potassium chloride, cesium chloride, and silver bromide. Once again, I repeat the examples: NaCl, KCl, cesium chloride, and silver bromide, AgBr. Then you see the note point. The note point is both Frenkel as well as Schottky defect is seen in case of AgBr. AgBr shows both Frenkel as well as Schottky's defect. Look at my question that is there on the screen. The question is, what type of stoichiometric defect is shown by ZNS? The answer to this is Frenkel defect. The second is, what type of stoichiometric defect is shown by silver bromide, AgBr? Both Schottky as well as Frenkel's defect is shown by AgBr there. So I hope I am very clear with these Schottky's as well as that of Frenkel's defect. The four types of defect I dealt with. The first defect I had dealt with, that is the stoichiometric defect, and in that stoichiometric defect it comes under point defect. Point defect is classified into three types: stoichiometric defect, impurity defect, and the third one is non-stoichiometric defect. I dealt with the first stoichiometric defect that was classified into four types there. The first one was vacancy defect, the second one was interstitial defect, the third one was Frenkels defect, and the fourth one was Schottky defect. The question comes from these defects there. Differentiate between Frenkel and Schottky defects. You will show with the help of the diagram and differentiate along with that of the examples also. Next video, I'll be dealing with the impurity defect, the second defect, as well as the non-stoichiometric defect in detail. I hope today's video was very clear. Thank you.